What are some of your favorite hobbies outside of school?
It's mostly video game based things. Sometimes I just like figuring out the little intricate mechanics of different systems. Tear something down to its finest parts.
Yeah.
Build something anew from it.
In our video, we will focus on the oil-filled boundary between the piston and the cylinder head, and how we know this is an effective design for reducing friction and wear inside the engine. This is a two-stroke engine. That means a power cycle is completed in one up and down movement of the piston. When the piston is at the top of the stroke, a fuel-oil mixture enters the crankcase through the carburetor, and as the piston travels downwards, this fuel-oil mixture is pushed up through a transfer port into the combustion chamber. At the same time, combustion products leave the combustion chamber through the exhaust. Once the cylinder returns to the up position, the fuel and oil are compressed and the spark plug initiates combustion, forcing the piston down and starting the cycle again.
For analyzing the lubrication flow around our cylinder, we'll be using the Navier-Stokes equation. This equation effectively is the conservation of momentum equation that also takes into account the viscous term.
So for the Navier-Stokes equation, we're going to make some assumptions to begin. So first, we're going to assume that our flow is coet, which means it's velocity driven, as well as the fact that our flow is unidirectional. So we'll have no velocity in the y and z directions, which means our gravity term will cancel. So we treat this flow as a coet flow, unidirectionally acting in the horizontal. We have two parallel plates, one of them being fixed and motionless. We'll say that is our bottom plate, and one of them, our top plate, is moving. So in our scenario, our bottom plate is our cylinder head, and our top plate is our piston head. If we take a control volume analysis of the flow going into and out of our parallel plates, because this is unidirectional in the x direction, this gravitational term will go to 0.
Well, first of all, since we are dealing with a developed flow far away from the boundary, it is in a steady state. So our acceleration term, that is the velocity change with time, goes to 0. Now let's look at the momentum flux term. Well, first of all, we know that the velocity is the same on the inlet and the outlet of our control volume, which means that the momentum flux into the system is 0.
The gradient of the pressure is equal to the viscosity times the Laplacian operator of U. Since we're assuming in the x direction that the flow is constant, this term goes to 0, and we have no out-of-plane flow, so this term also goes to 0.
Our pressure gradient also goes to 0 because we're assuming the flow is a coet flow, which means that our fluid is driven by this change of velocity between these plates rather than a pressure gradient.
After canceling out the terms of our equation using our knowledge of fluid mechanics, we are left with a single second-order differential equation which denotes our velocity distribution. Integrating this equation twice gives us our velocity as a function of y, but in order to do that, we need to know our boundary conditions, which are determined by h, which is the tolerance between the piston and the housing, which is 3 thousandths divided by 2. Also, the velocity at the bottom is 0, which gives us our final velocity equation.
Now that we know the velocity of our fluid, we can find the Reynolds number. Given the RPM of a typical Weedwacker, as well as the displacement of the piston head, we can get the velocity of our fluid. Relate that to the Reynolds number, knowing that in this small area between the piston head and the cylinder, we have just oil, we have the density of oil, we have the viscosity of oil, and our characteristic length, given by the tolerance between the piston head and the cylinder, we get the following Reynolds number of roughly 43, which is much less than 1,000, meaning our flow is laminar.
Because we have a low Reynolds number and meet the criteria for laminar flow, our skin friction will be less than that for turbulent or transitional flow, and that makes a good lubrication flow for our piston.